Bismillahirrahmanirrahim. Allahumma salli ala Muhammadin wa ala ali Muhammad. Dear students, I'm, as you know, Abda Hamid, Associate Professor of Chemistry. And today our topic of discussion is isomerism. And particularly, we will focus on enantiomers. What is isomerism? The relation of two or more compounds, radicals or ions, that are composed of same kind and number of atoms, but they are different. How they are different? Structural arrangement. They are different in structural arrangement or in arrangement of their atoms in space. Dear students, we will now discuss one by one all the types of isomerism. Uh, some are present in the syllabus of first year and some are present in the syllabus of second year, but both collectively you will face questions from all of these isomerism in your examination, MCAT वगैरह, MDCAT वगैरह, etc. etc. जी, isomerism may be of two types, structural, and structural is further divided into chain, positional, functional, metamerism, tautomerism, and right chain. The second type of isomerism is called stereoisomerism, while stereoisomerism can be further divided into configurational isomerism and conformational isomerism. First of all, we will discuss, we will focus our attention on configurational, which are of again two types, optical isomerism and geometrical isomerism. Dear students, structural isomers differ in their connectivity, means the different isomers have different type of connection. For example, look, this is a carbon chain and your group or branch may be attached with this carbon number 1 or with carbon number 2. That means connectivity is different. In one isomer, it may be attached with one carbon. In other isomer, the any group may be attached with carbon number 2. Similarly, stereoisomerism, how stereoisomerism is different from the structural isomerism? As you have seen, in structural isomerism, connectivity of the group changes. It may attach with one carbon, may attached with second carbon. But in stereoisomerism, we will say connectivity remains the same. Just orientation in the space changes. Look, whether the group attached may be orientated in this way, and in second isomer, this group may be orientated in this way. You can see here, connectivity is with the same carbon, carbon number 2, but orientation in space has changed. Similarly, it may be down or may be up. These two isomers will be different and they will be stereoisomer of one another. Now we will come toward the stereoisomers. Stereoisomers are of two types, geometric isomers and optical isomers. While Optical isomers again of two type, enantiomers and stereoisomers. Geometric isomers also of two type, cis and trans. We will discuss in details. So, geometric isomers. These isomers occur where you have restricted rotation somewhere in a molecule. And this is mostly present in carbon-carbon double bond, where a molecule, or it is also present where a molecule has ring or carbon-nitrogen double bond. There is also present restricted rotation. And the condition, important condition is the two carbons, those are bonded with double bond, should have further two groups different. Two groups attached with each carbon must be different from one another, otherwise it will not show a geometric isomerism. And we will understand now what is meant by restricted rotation. Look at this molecule of methane. It is rotating, and we can say it is freely rotating. So single bonds can rotate in free manner. And here it is an alkane, particular name may be, it is ethane, two carbon compound. Look how bond is rotating. Freely bond of alkane may rotate, single bond may rotate freely. So the isomerism which is evolved from the free rotation of sigma bond is called conformational isomerism. This atom is coming here, one isomer, then come here, second isomer, then third type of position, fourth position, fifth position, and sixth position. So this type of free rotation may also have different type of spatial arrangements which are called conformers, and the isomerism is called conformational conformational isomerism. But we will focus our attention on geometric isomerism and optical isomerism. So as we have already discussed, double bond between carbon-carbon show restricted rotation. Free rotation is not possible across this bond. So, due to this restricted rotation, only there are two possibilities. What are these possibilities? Look on this molecule, carboxylic group is present with both carbons. In this molecule, you can note carboxylic group is present on opposite side, same group are present on opposite side. So such type of molecules, when similar groups are present on opposite side, are called trans isomers. This is trans butane dioic acid. Its common name is fumaric acid. And when the both similar group are present on same side, then it is termed as cis isomers. For example, the cis isomer of butane dioic acid, in here is present double bond, butene dioic acid is called maleic acid. You can note here that the similar group, because are present on opposite side, so the vector sum, the pull of from this side and this side cancel each other. So this molecule become non-polar because of the equal pull of the electron by this uh, side and this side. While the cis isomer of geometric isomers are polar because here both are present on same side. It is not being cancelled, so these are polar. Similarly, you will note this is a stable compound because bulky groups are present on opposite side. But this is not so much stable like trans because bulky groups are present on same side. They have steric hindrance. Hindrance due to space is called a steric hindrance. So this is less stable than the transform of the geometric isomer. Dear students, we will discuss an important point here about these geometric isomers. These two isomers have different physical and chemical properties. As I told you, one is more stable, one is less stable, one is polar, one is non-polar, etc. So geometric isomers have different physical and chemical properties. Now we will discuss optical isomerism. Optical isomers are named because of their effect on plane polarized light. Simple substances which show optical isomers exist as two isomers known as enantiomers. First of all, we will learn some terminologies. What is plane polarized light? What is plane of symmetry? What is meant by the term chiral? What is meant by the term achiral? And what is light? Students, chir mean handness. Handness. Our two hands are similar to one another, but they are different. If we will put one hand on the other hand, you will notice our thumb will be on the little finger of the other hand. And we also know our one hand is mirror image of the other hand. It's mean our hand is not superimposable on its mirror image. Similarly, there are molecules which are similar. Both molecules are similar, like two hands. And these are similar in the way that one is the mirror image of the other. But they are not superimposable. If we will look at this molecule, if we take up it and we keep it here, this R group will be on the edge. So these are not mirror images. So Kair is from handness. This molecule you can note here has plane of symmetry inside it. Why? Because if we draw a line in the center, the molecule is divided into two equal parts. But look at this molecule. This molecule does not have any plane of symmetry. When there is no plane of symmetry, this is called chiral molecule. A chiral molecule is have no plane of symmetry. A molecule which have a plane of symmetry is described as achiral, while a molecule which has no plane of symmetry is described as chiral. Now students, look, this darkness when sun appears in the morning, what happens? Sun releases radiations, and we can notice these radiation in the color, in the white radiation. So our day becomes bright due to these radiations which are emitted by the sun, and we receive these on the earth. And you can note here that these radiations are of different wavelengths, and some are of higher wavelength, and some are smaller wavelength. So these radiations, when come collectively to us, we see a white light. But when we pass this white light, this converts into 7 colors Vibgauer. So the radiations uh, basically coming to us are linked with some colored energy. So radiations are coming, some are blue, some are uh, yellow, violet, indigo, etc. So first of all, we will learn that how we will get a single wavelength, because the light is a mixture of wavelength. So we will use monochromator. Mono mean one, chromator mean color then. So look, we will take this light, white light will fall on monochromator and reflect back, and when it falls on a screen, we will just provide of on opening on that place which color we require. If we require blue, then we give here opening. If we green here, if we want yellow, we will give here opening. So we use so we can get a single wavelength from this monochromator. And polarized waves are light waves in which the vibration occur in a single plane. To process, yes, we have seen that we have taken a single wavelength. Now we will polarize it. And how we will polarize it? Look here. A compound which does not rotate the plane of a polarized light is called optically inactive. For example, this plane polarized light is passing through this solution, but this is passing without rotating its direction toward right or left. So this type of compounds are optically inactive. But if a compound rotate the plane of polarized light clockwise, for example, it is rotating it clockwise, it is called a dextrorotatory compound. And if a compound rotates plane of polarized light toward left, it is known as levorotatory compound. It is also shown by the symbol, negative symbol, or L, and while dextrorotatory also shown by the positive sign of positive and or D. Now we will see what is the difference between the two optically active compounds which can rotate the light toward right or left. Why one is rotating toward right and why other is rotating toward left? Look here, this is tartaric acid. This carbon is a what do you say? Chiral carbon. Why carbon? Why it is chiral? It has all the 4 groups different. OH, H, COH, and this is a different group. This carbon is a chiral carbon. So, you can check here what is the difference between these two uh, isomers of the tartaric acid. This is positive tartaric acid and this is negative tartaric acid. This is dextrorotatory, this is levorotatory. And what is the difference? In this, OH group is on right side, in this on left side. In this H on right side, in this on left side. So this simple little difference makes them to rotate the light on opposite sides. Students, now we will see diastereomers are a type. What are diastereomers? These are isomers, a type of a stereomers. It occurs when two or more stereomers of a compound have different configuration at one or more of the equivalent stereo center and are not mirror image of each other. These two isomers of the tartaric acid. These two have this is also tartaric acid. This is also tartaric acid. In this, you can say, see, notice here, both OH group is on right side, and the this half molecule rotates the plane polarized right light right side, and this rotate plane polarized light on left side. Because both are mirror images of each other, so they rotate opposite side, light on the opposite side. So this molecules overall becomes optically inactive because the both uh, half centers, half parts of this molecule are rotating light on opposite sides. This type of isomer is called mesomer. Similarly, if both OH is on left side, again same condition appear. This upper half is the mirror image of the lower half. So this rotate light on the right side, this rotate light on the left side. So what happens? What happens? The overall molecule becomes optically inactive because it will rotate, it will try to rotate right, it will try to rotate left. So on the whole, these two molecules of the tartaric acid are mesomer. They are optically inactive. While we have seen in the previous slide, these are also tartaric acid molecules, but these are optically active. One will rotate plane polarized light on right, other will rotate plane polarized light on left. So we have noticed here four types of isomers of the oxalic and tartaric acid. Some are optically active and some are optically not active. Similarly, this type of these are the diastereomers of the enantiomers. These are optically, collectively, you can say enantiomers are relative to diastereomers because they have same molecular formula, but these are optically inactive, and while the enantiomers are optically active. Dextro and levo isomers are called enantiomer, while these are called diastereomers because these are optically inactive. Uh, Here is another point. If we will see, we will take a mixture of 1 mole quantity of this dextrorotatory and 1 mole quantity of this levorotatory tartaric acid, and we will mix together, keep them in a solution form, and we will pass. If we will pass a plane polarized light, this mixture of these 1 molar isomers will become optically inactive. Why? Because one isomer try to bend the light on right while the other on the left. So overall, there will be no effect, and this type of mixture is called a racemic mixture. Dear students, similarly, in a cyclic compound, there may also present uh, optical isomerism, and optical isomerism we will see in further example. But here are some examples of geometric isomerism, which is also a type of stereoisomerism, that in cyclic compound, you can note if the similar groups are on opposite side, then it will trans 1,2-dichlorocyclopropane. And here you can note here similar group on same side. So this is cis 1,2-dichlorocyclopropane. Dear students, you have seen, you people know that ibuprofen is a common painkiller. It has also two stereoisomers designated R and S, ibuprofen, which are mirror images of each other with different spatial arrangement of atoms at a chiral center. S and S enantiomer, also known dextrorotatory ibuprofen or positive ibuprofen, is the pharmacologically active form that provide anti-inflammatory and pain-relieving effect, while ibuprofen is synthesized as a racemic mixture. This is the formula of ibuprofen, your ibuprofen tablet, ibuprofen solution. This carbon, this carbon is the chiral carbon. You can note here, in one case, hydrogen molecule is away or in front of us, and in second, the methyl group is on in front of us, and hydrogen is away. So these two are positive and negative, or dextro or levo-rotative forms of ibuprofen. Uh, and properties, if we will note, optical isomers have same physical and chemical properties. As we have noted, geometrical isomerism has different physical and chemical properties. Optical isomers have same physical and chemical properties, such as density and melting point, except these rotate plane of polarized light in opposite direction. They show different physiological effect in human body. For example, limonene, a colorless liquid, it is abundant in essential oils of pine and citrus tree and used as a lemon-like odorant in industry and household product and as a chemical intermediate. So you can note here, students, that this is positive form. This is positive mean dextrorotatory, and it is levo form, negative form of the, and this carbon is the chiral carbon here in limonene. In one is isomers is opposite in the way of rotating of polarized light. Limonene exists as two chiral isomers or enantiomers known as dextro and levo. These stereoisomers have the same molecular formula but different spatial arrangement of the atom, leading to distinct smell and properties, with R limonene providing the scent of the oranges and S limonene, dextro and levo having a lemon-like aroma. Dear students, limonene exists in two isomeric form. Levorotatory limonene, the isomer that rotate the plane of polarized light, counterclockwise, and dextro, the isomer that cause rotation in the opposite direction. In the extraction of citrus juices, dextrolimonene is obtained as a byproduct, and it is also occur in carve oil, while uh, levolimonen is present in pine needles and cones.